Okay, so let's talk about the six trig functions. We developed sine and cosine on Friday, and maybe Wednesday a little bit as well. So let's write down our trig cheat sheet. I like to write this down basically before we get started on any trig problem. And I encourage you guys to do the same. So before you start your homeworks, before you start a WebAssign, practice just writing down your reference sheet. So always draw our triangles. Usually draw them in this standard position relative to a coordinate frame. We've got two special triangles. Our 45, 45, 90, which has sides 1, 1, square root of 2. And then the other one. Short side's 1, long side's 2, other side square root of 3. We're not actually going to use these much today. We'll get to these on Wednesday and use these a bit more, but we did introduce them previously, and I like to just write them down just to start ingraining them into your memory. And then the identities we've written down. So Pythagorean identity, which we can also solve for r if we want. And then we started off with sine and cosine. So sine was opposite over the hypotenuse, y over r. Cosecant was adjacent over the hypotenuse, x over r. And based on the triangle we drew, well, we can compute more ratios. We saw that because it's a ratio and because similar triangles will have the same ratio of sides, it doesn't matter how big we draw the triangle. As long as that interior angle is the same, they will have the same ratios. And this holds for any of the ratios we want to check. Well, there's three sides. We can come up with a lot of different pairs of sides to choose from. Right now, we've only chosen the, I guess, the coordinate sides relative to the hypotenuse. But we could also define another function. So our tangent function is defined as the ratio of the adjacent to the opposite side. So that's going to give us y over x. So sine and cosine are the big ones. They are essentially the building blocks for all the other ones. If you know sine and cosine, you can compute all the other ones. Tangent's a useful one to have. And so beyond sine and cosine, these are going to be the main three that you're going to want to make sure you know. Opposite over hypotenuse, adjacent over hypotenuse. Make sure you know how they're defined. The other three are essentially just the reciprocals of those. We have cosecant, secant, and cotangent. Cosecant is the opposite of sine, so hypotenuse over the opposite side, r over y. Secant is the reciprocal of cosine, hypotenuse over adjacent, r over x. And cotangent, wait, did I label those wrong? I did. No one's catching me on my trig. So tangent, opposite over adjacent, y over x. Cotangent, adjacent over the opposite, x over y. Just be careful with cosecant and secant. Sometimes it's easy to flip it. Your brain wants to assign cosecant with cosine because they both start with co. So remember, it's always the opposite. Cosine pairs with secant, cosecant pairs with sine. And by pairing, I mean they're essentially they compare the same sides, the opposite side and the hypotenuse. It's just, do I want to compare opposite to hypotenuse or hypotenuse to the opposite, depending on which one you want in the numerator and denominator. So some of the basic identities we have, these other three on the right can essentially be determined from these three on the left. So formally, this cosecant is 1 divided by sine. This is what we meant by the reciprocal. All I did was take this ratio and take 1 divided by that, which flips the fraction. Likewise, secant is 1 over cosine, and cotangent is 1 over tangent. Then some other things to note are tangent of theta, we can actually compute as sine over cosine. Because sine, well, it's y over r. Cosine is x over r. And if we are dividing by a fraction, that's the same as multiplying by the reciprocal. So we get y over x. And then likewise, cotangent is going to be the reciprocal of that, so cosine over sine. So sine and cosine are the building blocks, essentially, for all of the other trig ratios. One thing to remember is the mnemonic device. So if it helps, I'm not sure if anyone's seen this in high school. The common saying is SOHCAHTOA, which just means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is the opposite over the adjacent. So as we get going, I'm not going to continually write out this whole cheat sheet. Usually my trig cheat sheet consists of maybe those two triangles and then maybe the Pythagorean theorem or some of the other identities that we'll eventually get to. But like this chunk of how the functions are defined, hopefully that'll be ingrained into your memory here soon. And you won't have to rewrite that out. You won't need to reference it. And this can be a little tip to help remember it. So real quick, I want to actually talk a little bit about the domain and range for these functions. At least the first three. The domain for sine and cosine is minus infinity to infinity. Excuse me. The reason being, if we have an angle, even if it's somewhere over here, say, and our angle wraps around, then I can compute the sine and cosine of that angle based off of the projections that this angle makes with the coordinate axes. Namely, if we always project perpendicular to the x-axis and form a triangle, we can get side lengths based off of the x-coordinate and y-coordinate. And even if that angle keeps wrapping around, no matter how big the angle gets, remember, angles bigger than 2 pi just mean we're wrapping around the circle. Negative angles just mean we can do the same thing, just wrap around in the opposite direction. So it doesn't matter how many times we wrap around, nor in which direction, we can always compute a sine or cosine. And this is primarily because what is happening, so sine and cosine are y over r and x over r. The radius of the triangle we always consider as positive. And oftentimes we will normalize the radius to be 1. And so we can kind of imagine this bar here formed by this angle and rotate this end around. And the length of this is always going to be positive. It's always going to be fixed. So the denominator in sine and cosine always positive, which allows it to be defined everywhere. However, because the hypotenuse of the triangle is always the biggest side, well, that's in the denominator of sine and cosine. And so since it's the biggest side, sine and cosine are always going to be fractions. The absolute value is always going to be less than 1. So our range, so I should say less than or equal to 1, is going to be minus 1 to 1, including both of those endpoints. Tangent, on the other hand, is going to be different. It's going to be weird. The domain I'm going to write it in set notation just because it's a little wonky. So theta cannot be odd multiples of pi over 2. And what's going on with that? So pi over 2 is a 90-degree angle. Pi over 2 is this vertical side. And you can kind of see what's going to happen if I take this and swing it. The x value is going to get smaller and smaller. So we can draw another picture here. You can imagine an angle as we get closer and closer to 90 degrees. How big is that x side? And as I swing this edge up, this side, the x side of the triangle, is going to go to 0. And that's problematic because x is in the denominator for tangent. So whenever that denominator is 0, it's going to be undefined. And this occurs whenever we are at a vertical angle, whether it's the positive y-axis or the negative y-axis. And those are going to occur at odd multiples of pi over 2. And we'll get a little more into this on Wednesday and how to count in these fractions of pi. Our range, though, for tangent, minus infinity to infinity. Okay, so let's see a couple problems here. Let's say the terminal side of a triangle passes through the point, let's say -6, -4. I guess I should say not of a triangle, but of an angle. Evaluate the 6 trig functions. So they're close to getting to be like word problems. I don't know. Some people may not consider these exactly like word problems. They're leading in up to it though. And certainly in calculus, you'll be dealing with more situations where you're just given information that they describe in words, and then you yourself kind of have to paint the picture, figure out any sort of geometric relationships that are going on. Here we are just dealing with an angle, and we are told the side. So first step with all these problems is always going to be to draw a picture. So we've got -6, -4. And that's going to be our terminal side. Initial side's always on the x-axis. And we want to evaluate the 6 trig functions. So what we do, always draw the triangle perpendicular to the x-axis. So that way, this side is y, and this side is x. Specifically, though, we actually have the size of them. So let's say our x is -6, and our y is -4. So normally in triangles, if you're just given a triangle, we don't want to consider the side lengths as negative. But when we have angles, and particularly angles that are now given in the coordinate plane, there's a relative positioning going on. So because we have coordinates, the x side has coordinates -6, or has length -6, and the y side -4, because we are going negative on the x, negative on the y. And we want to take that into account when we evaluate these trig functions. So sine of theta is going to be -4 divided by the hypotenuse. So first thing we actually probably should have done, let's go ahead and compute that hypotenuse. R squared is -4 squared plus -6 squared. So 16 plus 36 equals 52. R is always positive. So x and y allowed to be negative, R always positive. Square root of 52, how do we simplify square root of 52? So you always want to try to factor these numbers if you can. 52, you can divide by 2. You can actually divide by 2 again. If you play cards, there's 52 cards in a deck, and there's 4 suits. 13 cards each suit. So our R we can write as 2 square root of 13. And now when we compute sine, we'll get -4 divided by 2 square root of 13. Simplifying, -2 over square root of 13. Cosine, we'll get -6 over 2 root 13. So -3 over 13, root 13. Tangent, we get opposite over adjacent, so -4 divided by -6 gives us 2/3. And then the other 3 we can actually compute by taking a reciprocal of the ratios. So sorry for not lining it up here on the notes. Let's do cosecant next. Remember, cosecant is just the reciprocal of sine. And because we've already computed sine, I can just flip those numbers. And that's what we get for cosecant. So negative square root of 13 over 2. For secant, we just flip cosine. And then the last one, cotangent, we flip tangent. Any questions on that? So you can always compute these guys if you want to use from your formula sheet based on the ratios of sides. You would do that again and then make sure you're simplifying them, and they would reduce to what we found here. Okay, so let's do one more example. Let's say the terminal side of an angle coincides with the line two x plus 6y equals 0, where x is less than 0. Compute the six trig ratios. So let's go ahead and draw a picture again. How do we plot this line? Let's go ahead and solve for y. So we'll subtract the 2x, divide by 6. So y is minus 1/3 x. So we've got our line. However, one side of the angle, remember, is always a ray. It's always on the x-axis. The other side is going to be on one of these sides of the line, and it tells us that where x is less than 0. So the side of the line we want is the left side of this line. So our angle is this guy here. And we want to compute the six trig ratios based off of this angle. So how do we do that? Well, in the last problem, if we have a point that lies on the terminal side of the angle, then we can compute them all. And on last week, we saw that, well, it doesn't matter how big the radius is. So we can pick any point on the terminal side to compute these ratios. So let's pick a point. How did I find this point over here? Well, I just used the slope. The origin should be pretty clear that we pass through 0, 0. And since the slope is negative 1/3, I went left 3 and up 1. In other words, I went negative 3 on the x, positive 1 on the y. And this point is negative 3, 1. The hypotenuse then so hypotenuse square root of 10 And now let's go ahead and compute all the sides. So sine of theta is going to be 1 over square root of 10. Cosine theta is the adjacent side, so negative 3 over square root of 10. Tangent opposite over adjacent, 1 over negative 3, or negative 1/3. Cosecant theta, 1 over sine, so square root of 10 over 1. Secant, square root of 10 over negative 3, or negative root 10 over 3. And then cotangent, 3, negative. So negative 3 over 1 in that case. Any questions on that?
I actually have one question. I think you said something about it earlier. Which side is the is like considered the terminal side?
It's always the side that's swinging around.
Okay.
One side's always the positive x-axis. The terminal side is the other side that you think of
Okay.
like a hand on a clock or something rotating around.
So like would it always sorry, would it always be considered like the hypotenuse?
Yeah.
Or is that not okay?
No, terminal side is always the hypotenuse, exactly.
Thank you.
I did another question real quick. So since we have a line that goes through both sides of the coordinate grid, how do you know which side of the grid to use for your triangle? Because you could just as easily have a triangle in the fourth quadrant as you would have one in the second quadrant.
Yeah, exactly. And then we'll actually see that on today's in-class activity, where we have to give you some other extra bit of information to know which side of the line you're on if we give you information about a line coinciding with the terminal side, and specifically from this part of the information.
Okay.
So it'll be an exercise today on the in-class activity where you'll do both sides, and then you'll compare the trig ratios and see how they differ, see how they're similar. So one thing to note is here I had an angle and it's in the second quadrant. What ratios are positive? Sine ended up being positive because we're still vertical on the y-axis. But cosine and tangent ended up being negative. And then likewise in the last problem, when we had an angle in the third quadrant, what happened with this guy? Sine and cosine both ended up as negative values. But tangent, the negatives canceled and we got a positive value. And of course, the reciprocal trig functions, they're going to always have the same sign as their corresponding function in the first three. So we'll talk more about this on Wednesday, and this is going to be a general pattern that based off of where the quadrant is, we can actually determine which trig ratios are going to be positive and negative. And it'll be another tool for us to use as we evaluate these trig functions on our special triangles and where those special triangles might end up now in a relative coordinate frame if they're in the third, fourth, second quadrants.